All right, guys. Um, Sorry about the break in the video, um, but maybe that's good to give you a chance to process things. All right, so we were talking about different types of energy, and first we talked about types of energy based on, um, I guess, what is doing the movement. Um, And then we got to kinetic and potential energy, which is describing energy in terms of is it a static energy or a stored energy, which is potential energy, and or is it a dynamic kind of energy, the energy of movement, which is kinetic energy. And in fact, just like um, the types of energy based on what is actually doing the movement, where we're talking about electricity, which is electrons moving, or light, which is photons moving, or heat, which is molecules moving, and these are all interconvertible. Kinetic and potential energy are constantly going through cycles of conversion. And so um, it doesn't matter what you're talking about that is involved in the energy, whether it's heat energy or mechanical energy or light energy. Um, these are always going through one stage um, in a kinetic type of energy, and then the next stage in the potential energy. And so, a couple examples of that are, for instance, molecules. So, when you're talking about chemicals and chemical reactions, the molecule itself represents potential energy. All molecules have a potential energy, how much energy is stored inside their chemical bonds. And when those molecules undergo a chemical reaction, that's when they're exhibiting kinetic energy. So if you think about ATP hydrolysis, so right here, this is ATP in the corner, and when this bond is broken, that's kinetic energy. So the atoms and the electrons within that molecule are rearranging themselves, and so that's a kinetic form of energy. And so the the ATP hydrolysis, the energy in the bonds of the ATP are then going to be transformed into some other form. Maybe it's going to be transformed into the movement of a transport protein, or maybe it will be um, transferred into the um, um, the chemical bonds of another molecule. So another example of the cycle between kinetic and potential energy is like this rock on a hill, where it takes energy to push that rock up to the top of the hill. Once it's at the top of the hill, then it's got potential energy because of its gravitational position. If you push the rock off the top of the hill, it will release that potential energy as kinetic energy as it moves down to the bottom of the hill. Okay? Or like this girl on the swing, she needs to pump her legs in order to move the swing. But then once she's moving at a certain speed, then she's got that kinetic energy. So different types of energy are being converted, not just between um, mechanical energy to heat energy or light energy to chemical energy, but also between kinetic and potential forms. All right, so let's just really quickly look at those basic types of energy. So heat energy is the motion of molecules. So if molecules are moving very quickly, they're hotter, right? So like gases. So if you think about gaseous water, you have steam. Steam is very hot. If you have um, steam, the water molecules are moving very, very quickly. On the other hand, if you have solid water, if you have ice, then you have very cold temperatures and you have a very ordered crystalline matrix, and the molecules are moving very slowly, like you see in this central picture here, where they're vibrating, but they really don't have the freedom of movement. When you have liquid water, you have an intermediate temperature, like you see contained here, and the molecules are moving um, at an intermediate rate. So the faster the um, the molecular movement, the more heat you have, and the more movement, you also get more Brownian motion, so you get more diffusion. Light energy is the energy of the movement of photons, and there are photons that occur in many different wavelengths. So the higher the frequency of the wavelength, so the shorter the wavelength, the more energy that photon possesses, right? So you've got different kinds of photons. There's photons of visible light, which are the red, orange, yellow, green, blue, purple, but you also have low energy photons like radio waves and high energy photons like X rays and gamma rays. And these are capable of um, changing molecules, the high energy photons. Visible light is a very special part of the electromagnetic spectrum because visible light is energetic enough to cause changes to many molecules. For instance, pigments can absorb visible light and cause um, and the molecules can change. But they're not so energetic that they destroy molecules, right? Things like X-rays and even UV rays are capable of actually causing um, huge chemical reactions or ionization even, and that becomes very dangerous to biological systems. All right, so one of the things that is useful in chemistry and also in biology is to know what way will a reaction spontaneously occur. And one of the concepts in um, predicting which way a reaction will be spontaneous is equilibrium. Um, so all reactions are spontaneous. If a reaction happens, then it's spontaneous. But sometimes you have to have an additional source of energy in order for it to be spontaneous. So when we describe the reaction of, or let's say glycolysis, glucose is going to be split into two smaller sugars, which then become pyruvate, and you make ATP in the process. But you can't, you know what, that's a bad example. Let's talk about putting glucose together to make starch. Okay, so um, just taking a solution of glucose, um, it's going to be pretty unlikely that you'll spontaneously form starch. But if you add ATP to that system and the proper enzymes, then you can make it spontaneous, right? But you have to add the ATP to make it spontaneous. So while just adding glucose um, together to make starch is not a spontaneous reaction, glucose in the presence of ATP to facilitate the reaction is a spontaneous process. Okay, so you see that you're making it spontaneous by changing the reaction conditions, by adding ATP. Um, so when you look at equilibrium, equilibrium is the state where the forward reaction is occurring at the same rate as the backwards reaction. And it doesn't mean that your products and your reactants are equal. It does not mean that. It means that the forward reaction is happening at the same rate as the reverse reaction. All right, so let's look at that in a little bit more concrete terms, right? It's kind of hard to think of A plus B going to C plus D, but let's look at equilibrium in terms of diffusion, because I think diffusion is a little bit more visual of a concept. So if you look at this system that's illustrated in this first panel, this is the beginning of our reaction, which is the diffusion of these molecules across this membrane. So initially, um, the the what do I want to say? The system is very far away from equilibrium. Okay, so these molecules are going to begin diffusing across this membrane. So the reaction is going in what we're going to say is the forward direction, the movement of these molecules to the other side of the membrane. Eventually, you're going to have as many molecules on the original side of the membrane as on the new side of the membrane. And this is the point where we've reached equilibrium. But I want you to notice that the reactions haven't stopped. The molecular movements have not stopped. Okay? You still have molecules moving from this side of the membrane to this side of the membrane. But you also have molecules moving from this side of the membrane to this side of the membrane. So remember when we talked about entropy and we said in some sense, entropy is a sense of probabilities. And this is the same with equilibrium and chemical reactions in general. Here, there's no probability that molecules will move from this side of the membrane to that side of the membrane because there are no molecules there. When you get to this state where you still have the forward reaction occurring, these molecules on this side of the membrane can still move uphill. It's just less likely because there are less molecules. Once you've reached a state of equilibrium, however, there are just as many molecules here that can move through the membrane this way as there are molecules on this side of the membrane that can move there. So the rate at which the reaction is occurring, in this case our reaction is the movement of a molecule across the membrane, is equal. You have just as many molecules moving this way as you have moving that way. Okay? All right. I don't want you to freak out at the equilibrium constant, okay? But I do want you to understand what it means, and you should be able to calculate it because it's fairly simple. So if you have a reaction, A plus B as your reactants and C plus D as your products, the equilibrium constant is the ratio of the concentration of the products over the concentration of the reactants once equilibrium is reached. Okay, so KEQ, the equilibrium constant, describes a certain set of conditions only when chemical equilibrium is occurring, right? So if we go back here, you'll have a certain um, concentration of molecules here and a certain concentration of molecules here at equilibrium. That concentration is not true here. Sorry. That concentration is not true. Those concentrations are not true at the initial state, right? Because at the initial state, we are not at equilibrium. So it's only true, KEQ, the concentrations that you see at KEQ are only true when the reaction is at equilibrium. All right? Now this is useful because it allows you to predict um, the way a reaction will tend to go. Okay, now you have to remember that that equilibrium occurs under very specific conditions, right? Your standard conditions. So at room temperature with the same number of, the same concentration of of reactants and products that began at the initial conditions. Um, there's the atmospheric pressure. So all of those things have to be at standard conditions. Um, so if you look at this ratio right here, if you have more products than reactants at equilibrium, will you be greater than 1 or less than 1? If your numerator is greater than your denominator, you'll be greater than 1, right? So for instance, if you have more products, let's just arbitrarily assign the number 2, and you have less reactants, let's assign the number 1, 2 over 1, right? So that's greater than 1. So if KEQ is greater than 1, you have more products than reactants at equilibrium. So the forward reaction seems to be favored. Okay, you're producing more products than reactants at equilibrium. If the other way is true, if you have more reactants than products, so let's switch that scenario. We'll have our products as 1, and we'll have our reactants at 2. That's 1 over 2, or 1/2. That's less than 1. Then our reverse reaction is favored because we have more reactants than we have products at equilibrium. Okay? So you also have to keep in mind that some of this is semantics, right? Because if I'm interested in glucose becoming pyruvate, then my forward reaction is defined as glucose becomes pyruvate. But if I'm interested in the opposite, if I want to build glucose, say I'm talking about uh, anabolic processes, then I might reverse the reaction that I'm interested in, and I might say pyruvate becoming glucose. Okay, so some of this is a just semantic consideration. All right, so let's look at some of this. If the equilibrium constant is 2, then what is true? Okay, the answer to this is A. There'll be twice as much B as A. Because remember, KEQ is the concentration of B over the concentration of A. And if the KEQ is 2, then 2 over 1. There's twice as much B as A. Okay? So how does this help us when we're trying to determine whether a reaction is spontaneous? And this leads us to Gibbs free energy. Gibbs free energy represents um, the amount of energy that can be used for work. Okay, it's the useful energy, right? Because remember, some energy is not capable of being used for work in a system, like the entropy in a system. Um, so the change in free energy describes a process. So a way to think about free energy is if you're talking about just G, you're just talking about the Gibbs free energy of a molecule, for instance. That's a potential energy. When you talk about delta G, you're talking about the change in free energy. So something is changing. You're going from your reactants to your products. You're going from a rock on a hill to a rock at the bottom of the hill. Something is changing. And so when you talk about delta G, you're really talking about kinetic energy. And um, if there is no kinetic energy, if delta G equals 0, then um, you're at equilibrium. Okay, there's no change in the system. There's no energy available for work. There's no difference in the energy between the products and the reactants. All right, so um, the greater the change in free energy, the more ability for work you have. Okay, so a good kind of concrete example of that is if you drop a rock, if you drop a rock out of your hand, right? It's going to hit the floor, and you might scuff the floor a little bit, but you're not going to damage much. You might hurt your toe. But if you drop that same rock off of a skyscraper in Makati, you can kill somebody, right? Because um, there's a lot more potential energy in a rock at the top of a skyscraper than there is in a rock held in my hand. All right, so there's a lot more potential energy for work. Um, Another good example of that from a chemical state is Um, if you're um, what's a good example of that? You can burn a molecule of glucose, one molecule of glucose, um, and you might get a small fire, but there's not a whole lot in the glucose compared to a molecule of starch. You have a whole lot more fire in your starch. There's more potential energy there, right? So you can get more energy um, out of a molecule of starch than you can get out of a molecule of glucose, right? Or if you think about it in terms of your metabolism, you have to run many more kilometers in order to work off a molecule of fat than you do to work off a molecule of glucose because there's a lot more energy in it. All right, so this should be a review for you. This is just something you have to memorize, right? So Gibbs free energy, if the delta G is positive, you're going from your reactants being at a lower energy to your products being at a higher energy. This is an uphill reaction, right? You're going from low to high. So the change in free energy is positive. The change in free energy increases. You're increasing the amount of energy from the initial state to the final state. So positive free energies are non-spontaneous reactions. And you have to make those reactions spontaneous by coupling them to spontaneous processes like ATP hydrolysis. On the other hand, if you start out at an energy state that's higher and you end up in an energy state that's lower, then you have a negative free energy. Then your change in free energy is negative. You're going from high to low energy. That's a downhill reaction. That's spontaneous. There's energy available for other processes, energy available for work. So you should be able to speak about these terms in all of these ways. All right. If the delta G of a reaction is negative, is it going to be exergonic or endergonic? It's going to be exergonic. Exergonic reactions are spontaneous. Okay, now this one you might have to think about for a minute. If the entropy of a system decreases, then the reaction is exergonic or endergonic. So let's think about this for a second. Entropy of the universe should always be increasing. So if the entropy decreases, that means that I'm forming a more complex state. That means I'm going to need a kind of energy input. That means I have an endergonic reaction. Okay, if I'm forming an ordered state, that requires energy. If I want my room to be cleaned, I have to put work into it to put all the things where they belong. All right. So we've talked about which way a reaction will tend to go based on the equilibrium constant. Let's talk about which way a reaction will go um, in terms of the change in free energy and the concentrations of your products and reactants. All right, so we're looking at the reaction X becomes Y. Now remember, we said at equilibrium, delta G equals 0. That's right. So if you have no change in free energy, then your forward reaction and your backward reaction are happening at relatively the same rates, and you really don't have any capacity for work there. All right. So we're going to move away from equilibrium, and we're going to do that by adding more products. Okay, we're going to increase the concentration of X. And now we've moved our system away from equilibrium, right? Because equilibrium is a very specific set of conditions. So we've moved our system away from equilibrium by increasing the concentration of X. We've added more X, and that's going to push the reaction to the forward direction. Okay, we've added more X. Now this reaction is going to move back towards equilibrium. And so we need to get the ratio of the concentration of Y to the concentration of X back to KEQ. So by adding more X, I'm going to push the reaction into the forward direction so that that ratio goes back to here. All right? Now, on the other hand, if I add more products, I'm going to shift the reaction into the other direction. I'm going to shift the direction of the equilibrium to favor the reverse reaction. So if I add more products, then I'm going to move the reaction towards making more reactants. Okay? So this is actually a very powerful mechanism that cells use all the time in biochemical pathways, because in a biochemical pathway, you're always dumping more, you're making product from one reaction, and that's going to increase the concentration of that molecule, which is actually a reactant for the next reaction. All right, what is delta G if X goes to Y is at equilibrium? It's going to be 0. So if I add more reactant, will delta G become more positive, or will it become more negative? It's going to become more positive because I'm pushing, where's my mouse? I'm pushing the reaction in the reverse direction. If I add product, I'm moving in the reverse direction. That's non-spontaneous. Okay, so it's positive delta G. Right. So if I add more product, more products will become reactants. All right, so this brings us to a concept called the standard free energy change, which can also be called delta G naught. Right? Our book, a lot of books just use this little degree sign, and some other books use just this prime. Our book uses both of them. I'm not really sure why, but it all represents the standard free energy change. Now, the standard free energy change gives us a measure of delta G for all sorts of different reactions. You can look them up in a book. They've been measured. Um, but these are all at standard conditions. Okay? Standard conditions include 25 degrees Celsius, 1 atmosphere of pressure, the pH is 7, and the concentration of the reactants equals the concentrations of the products equals 1 molar. Okay? So are these the conditions that you see in a cell? No, obviously, because your body temperature is 37 degrees Celsius. So right there we know that these standard free energy measurements are not exactly applicable to biological systems. Okay, that said, they're still useful to look at biological reactions because it gives us a point of reference. Okay, so a good example of this is looking at ATP hydrolysis. At standard conditions, ATP hydrolysis is a spontaneous reaction, and it provides about 7.3 kilocalories per mole um, of energy that can be used for work. So delta G is negative 7.3. All right. So under standard conditions, the concentration of ATP is equal to the concentration of ADP. At standard conditions, you're at 25 degrees Celsius. But really, you have to consider the concentration. That's really the big one here. Because in a cell, the concentration of ATP is kept very high, and the concentration of ADP is kept very low. And this is going to change the delta G in the cell. And it's going to do what? Is it going to push the reaction forward towards the formation of ADP, or is it going to push the reaction backwards? If you add more ATP, then that reaction is going to be pushed into the forward direction. Okay, and in numerical terms, we see that instead of ATP hydrolysis being negative 7.3 kilocalories per mole, the delta G in the cell, because of the concentration differences, is negative 12 kilocalories per mole. That's almost a doubling, okay, and that's all primarily based on the concentrations effects of keeping the concentration of cellular ATP high and the concentration of cellular ADP low. So let's look at this in terms of a biochemical reaction. This is glycolysis, and I'm hoping everybody is very familiar with glycolysis. Um, we're going to use this as our study of glycolysis. So when we talk about aerobic respiration, I'm going to go right to the Krebs cycle. Um, so this is a typical biochemical reaction in that you have several key points along the biochemical pathway that drive the other reactions. So if you notice, oh, I have to stop again. My baby is crying. But this is a good place to stop. So